In this video, I'm going to be talking about stylometry. This is the idea that we can learn something about the relationships among documents based on how they use certain words at different frequencies. The techniques I'm going to be talking about are applicable to text written in any language, but I'll be explicitly discussing this in the context of Chinese literature. The goal is to think about how genres relate to each other stylistically. As such, I will discuss how to visualize textual relationships by comparing the relative frequency of terms, in this case the relative frequency of Chinese characters, using something called principal component analysis, or PCA. PCA is a linear algebraic technique that can be used to see the variance within the dataset in a manner that's easy to visualize. It will allow us to take a dataset that's highly dimensional, that is, a dataset that contains tens, hundreds, or thousands of different words at once, and reduce it into 2 dimensions so it can be presented on a screen. So let's imagine that we have a text, and we want to compare it with 5 other texts. Let's say that in these hypothetical documents, we've decided that the frequency of the words and of will tell us something meaningful about the relationships or differences among these works. Text 1 has and 6 times and of 7 times. Text 2 has and 10 times and of 14 times. Text 3 has and 8 times and of 3 times, and so on and so forth. We can rearrange these texts into a matrix where and is one column and of is the other column, and each text is a row. Let's look at just and first. We can look at the relationships among these texts based on how often and appears in each document by placing them on a simple number line. We can do the same thing with of, which leads to this rearrangement. We can also plot this in 2 dimensions to see the frequencies of ands compared to ofs. By doing this, we can see which documents are most similar to or most different from each other. This is a basic visualization of the relationships among these documents, but in the real world, the relative frequencies of and of are probably not going to tell us much that's actually meaningful about a corpus. We could add a 3rd term that we think will give us more information about the text relationships. Let's say the. It's still easy to visualize this using a 3-dimensional graph, although we can run into difficulties in reading such a graph when it's presented in a 2-dimensional form, such as on a screen. Think of this like projecting the spherical Earth onto a flat map. It'll always result in some distortion. Just 3 words will probably still not tell us much about the corpus at hand, so we can add a 4th term, it. We can mathematically calculate the distances among these documents because ways of measuring spatial relationships such as Euclidean distance, the straight line between 2 points, can be generalized into any dimension. But suddenly, we don't have a way of visualizing all of the data at once. Often, we'll want to look at many more than just 4 dimensions, 5 with he, 6 with she, and so on. Sometimes it's useful to study the 100, 1000, or even 10,000 or higher n most common words in a corpus to really understand the relationships among documents. So instead of plotting these texts on axes based on the frequencies of specific words like and of, we can use principal component analysis to calculate the variance within the dataset, and then to project the points representing our documents from a high-dimensional space based on more than 3 words into 2 dimensions consisting of principal components. This will allow us to see as much variance or difference among texts as possible based on how words are used at different rates in each work. Essentially, principal components are abstracted axes that account for a certain amount of variance within the dataset. The first principal component accounts for the largest amount of variance. In the case of the data that I'm about to show you, this first principal component accounts for about 24% of the variance across the entire dataset. The second principal component contains as much variance as possible after the first PC has been accounted for. Here it's about 4%. Each subsequent component represents a progressively smaller percent of the variance, 3.5, 2.7, 2.3, etc. After the 10th component, each represents less than 1% of the difference. So you see, you can dump lower PCs without losing too much information. As such, it's useful to look at just the top 2. In practice, what this means is we are reorienting the data set so we can get the best view of the differences among our texts. So now our x-axis is no longer and, but principal component 1. Our y-axis is not of, but principal component 2. As part of this analysis, we'll try to determine what the components represent in relation to our corpus of texts. That is, how do we interpret these abstracted axes? Because I'm interested in genre, I'll be showing you a figure in which texts are labeled according to their genre. I'll be analyzing the relationships among works of 3 different genres as labeled by the creator of the Wenxian Fanren 8 website, and this analysis is based on the 1,000 most common characters across the entire corpus. Each dot represents a chapter or scroll from a document. The blue dots are chapters from official histories. These are works that were vetted by the imperial government and discuss those historical events the government judged most important. The magenta dots are chapters from historical romances. These are fictional works based on actual historical events. In green are chapters from purely fictional works. Often these touch on history, but they largely focus on things that have no historical basis. This dataset consists of 13,250 chapters from 471 texts. When I plot these documents on the first 2 principal components, I get a figure that looks like this. You can see that official histories in blue dominate the left side of the figure. While they're not widely distributed on the x-axis, they are spread across the y-axis. Fiction, on the other hand, is densely concentrated on the right side of the figure and shows less dispersion across the y-axis. Historical romances in magenta are concentrated between the 2 other genres, essentially bridging the gap. To be able to properly interpret these axes, we have to look at how specific characters contribute to them. We can do this by looking at the component loadings, which show how each variable figures into each component. The further a character is away from the center of the plot, the more influence it has on the results. This means that the vast majority of characters don't actually tell us much about the differences among these texts. In the lower left-hand corner is the character zhi, which can have multiple meanings, but is often a particle marking possession in classical Chinese. This means that texts which appear further down and to the left on the plot tend to contain the character zhi at higher frequencies than those that appear in the upper right portion of the plot. Similarly, texts that appear on the right of the plot use the character de at a higher frequency than those on the left. This is interesting because de is essentially the vernacular counterpart to zhi. We can use the relative position of these characters as a way of trying to interpret what our abstracted axes represent. Let's just look at the first principal component. I'm going to spread them out to make it easier to see what's happening. What we can see is that, generally speaking at least, on the left portion of this component, we have characters that are associated with classical, formal language. On the right, we see more pronouns and grammatical particles that appear in vernacular and informal language. Essentially, this component can be usefully interpreted as a gradient from classical to vernacular language that accounts for a quarter of the difference among all of the texts in the corpus. If we look at the second principal component, seen here spread out again, we can see that the upper part of the y-axis is dominated by numbers, time words, and geographic locations. Perhaps unsurprisingly, the histories are spread out along this axis. So when we look at the original plot, we now have a way to interpret it. Novels tend to be more vernacular and use pronouns, and histories focus on time and geography in ways that are less common among fiction. We can plumb this a bit further by looking at the plot in one dimension at a time. I'll start with the first principal component. I'll divide the data by genre so we can clearly see their differences. This histogram shows the density of texts appearing along this axis, and here are the characters for reference. We can see that the histories are far more dominant on the left, the historical romances are fairly evenly dispersed, and the novels are most dense on the right. If we look just at the second principal component, we get a different view. Here, histories are the most widely dispersed, with historical romances and novels staying fairly well in the center of the plot. We can use the combination of these 2 axes to start to analyze and think about the broader stylistic relationships among these documents at the corpus level. Now the question is, how do we get from real language documents to dots on a graph? I've already mentioned that we're using frequency of characters, but how does this happen in practice? Let's take the case of the famous late Ming novel The Plum in the Golden Vase. Here we can see all 100 chapters of the novel. Let's look just at the first chapter. In its plain text form, it looks like this. David Todd Roy has translated the title of this chapter as Wusong fights a tiger on Jingyang Ridge, Panjin Lian disdains her mate and plays the coquette. To go from this to a document representation that we can study using linear algebra, we have to take a few steps. We start with vectorization. We want to take each document and turn it into something that we can spatially represent. Here I want to create a vector or point-in-space representation. I just want to count up how often every character occurs in this chapter. You can see here that we see D once, E once, Hui once, etc. We'll keep track of how often each character appears and how long each chapter is. You might wonder why I'm looking at individual characters, 1-grams, instead of words, or bigrams or trigrams. I do this because words are hard to determine in classical Chinese because the original documents lack both whitespace and punctuation, and the boundaries between words are often ambiguous. Bigrams and trigrams are useful in many cases, but they tend to obscure some of the more interesting relationships among documents that are dependent on grammatical particles that exist in single characters. For style, 1-grams seem to work quite well, but bigrams, trigrams, and higher n-grams can often distinguish texts based on content. Now in practice, this process is extremely fast, taking less than a millisecond for most texts. This results in a vector in which zhi appears 35 times, bu appears 164 times, e 161 times, and so on. We do this for every chapter in The Plum and the Golden Vase, and for every chapter in all the works in the corpus. Now we have what's known as a bag of words vector space representation of our corpus. This is called bag of words because I'm ignoring context. There are ways to account for this, but this model gets very good results. Now we have to consider how long each chapter is. You'll notice that chapter 1 is nearly twice as long as chapter 2. If there are big disparities in the lengths of the documents we work with, this will influence their apparent relationship. To take account for this in the case of zhi, we'll divide the raw number by the length of the chapter, in effect normalizing the count by returning a frequency. Now I'll multiply this number times 1,000 so you can more clearly see the differences, converting the frequency to frequency per 1,000 words. Then in turn, we can use this number to represent the character instead of the original raw count. There are other ways of normalizing, but this is one good way of doing it. And we'll do this same operation for every character. Essentially, we're now representing the corpus as a matrix. Each chapter is a dot in n-dimensional space, where n is the number of unique characters or variables representing the text. You can think of this as an m by n matrix, where m, the number of rows, represents the number of documents in the corpus, and n, the number of columns, represents the number of unique terms in the corpus. In practice, we'll limit the number of terms in this matrix because certain ones tell us more information about certain things. Common characters are useful for getting a sense of authorship and genre, while less common ones tend to reflect content. You can even set a specific vocabulary to analyze. In Chinese, we often ignore whitespace and punctuation because these were often added by later typesetters and don't reflect the original content of the work. So now we have this matrix. In the case of my corpus, it is a 13,250 by 1,000 matrix. Using principal component analysis, I can project this data into a new space where most of the variance is contained in the first two dimensions, principal component 1 and principal component 2. I can use this new coordinate system to visualize the relationships among the documents. We can take the new values for these first 6 chapters and place them back on our plot. You can see that yes, this is indeed from The Plum and the Golden Vase, and that this is part of our larger dataset. This is essentially how we can use principal component analysis to study the relationships among a corpus of texts. Thank you for taking the time to watch this video. I hope it was informative. If you have any comments or questions, please feel free to leave a comment below, and you can reach me on Twitter at pvirth. Thank you and take care.